Hi class, we are starting the next chapter, which is chapter 7. So chapter 7 is pretty much review. We go over a lot of the things that we are familiar with already. Subspaces, span, linear independence, those sort of things. We just kind of look at them through a new lens, okay? Now, however, this section, 7.1, this will be pretty new for most of you guys, pretty much all you guys actually. It's very proof orientated. In fact, the entire section is proofs only. So I don't want you to get discouraged. Really model your work after the work that you're going to see here. Now, this is going to be a formal proof modeling that we're going to see here. So you want your work to look as close to mine as possible. Okay. We are going to go through what are called vector spaces, and then after we're done covering vector spaces in this section, everything that we do for the remainder of the semester through this video series will have to do with vector spaces. Okay, so it's a very important topic. We've alluded to vector spaces quite a bit, but we haven't really talked about them in depth. We talked about a lot about subspaces. So a subspace is it's a subspace of a vector space. So we've talked about quite a few vector spaces already. We just haven't called them vector spaces. Okay. So our definition here is very axiomatic. There are 10 axioms which we need to cover in order to prove or verify or show that a space is a vector space. Okay. The first 5 of these properties, these axioms that we cover, will be related to addition, and the last 5 that we cover will be related to scalar multiplication. Okay, so it's always easier if you divide these things up. You're not going to have to memorize these, although you should be familiar with these 10 axioms already. Even if this was a regular exam that we take in class, I would provide these to you. Okay, so you should definitely know what these axioms are. The difficult part will be knowing how to prove these, right? So here is our definition of a vector space. Let V be an arbitrary, non-empty set of objects on which 2 operations are defined. So let's dissect this piece by piece. So by arbitrary, it just means that it is a collection of things, right? Which means that it's non-empty. Now these things, this set of objects that we have, doesn't really matter what they are. So far we've been calling them vectors because we're used to vector. We're talking about vectors, right? We will see throughout this chapter that this also includes things such as matrices, the real numbers, functions, those kinds of things. Linear transformations. We're now thinking of our vectors not only as a column of numbers, but as objects that satisfy these 10 conditions. Okay, so a vector space is a space of a collection of things that satisfies these properties, right? The properties that the operations that are defined on a vector space are the properties that we're used to: addition and scalar multiplication, right? So I also want to talk about this. Our definition of addition does not have to be the standard definition of addition. As long as it satisfies the 5 properties of addition that we'll go through, we can call that addition. Okay? Multiplication by scalars does not have to be what you regularly think of as multiplication. As long as our 5 multiplication axioms are satisfied, we can call that multiplication by scalars. Okay, so this is where it's going to get weird to you guys, because you're going to see things and you're going to be thinking about it in a very standard way that you're used to. However, we are going to really just kind of flip that upside down on its head. Okay, so I want you to come into this video with an open mind. Don't hold on to your standard notations of mathematics as you know them up to right now. Okay, so we're going to go over the following axioms. So again, it's split into 2 groups: 5 of addition, 5 of scalar multiplication. Okay, so we generally at this point would define what we want addition to be and what we want multiplication by scalars to be. However, this is a definition. So if the definitions that we define of addition and scalar multiplication are true for the following axioms, then V is a vector space. Okay, and the objects inside of that vector space are what we call vectors. Okay, so let's say we have 3 vectors inside of our vector space. So this shouldn't be a regular V like this one. I don't know why my program changed the values. But let's say we have 3 vectors, okay, u, v, and w. And let's say we have 2 scalars, okay. So every time you go through this proof for proving something is a vector space, you will need 3 vectors and 2 scalars. So make sure you say, hey, these are my 3 vectors and these are my 2 scalars. Okay, so that's what we have now. 3 vectors, 2 scalars. Such that scalar multiples of these vectors here are still in V. Okay, so these are the axioms. So again, first we're going to go through the addition, then we will go through the multiplications axioms. If I have 2 vectors in my vector space, then if I add them together, they will stay inside of that collection of objects that I have, right? So if I add any 2 objects that are already in my space, it will get me a new or one of the objects that are already in my vector space. So again, we've seen this before. Our verbiage for this is closed under addition, right? So the first axiom has to be that I'm closed under addition. So if I take 2 objects in my space and I add them together, I will still be inside of my space. Okay, so our second axiom of addition is that if I add 2 vectors together, u plus v, that it will be the same thing as adding them together in the other direction, v plus u. So it shouldn't matter which order I add things together. If that's true, then that is one of the axioms that I need for my vector space. So again, this is called the commutative property of addition. So if I'm closed under addition, if the commutative property holds. The third is that if I have u plus me adding these 2 together first and then adding it to u, right, order of operations, that should be the exact same as if I were to add u and v together first and then add in my w. So you may remember this property too. It has a name. It is the associative property. Okay, I gave you a pause there to hopefully you knew what it was. So the commutative property of addition, the associative property, meaning it doesn't matter which one I add together first. As long as I'm adding everything together, I should come out with the same thing. So closure under addition, commutative property of addition, the associative property of addition. For 4, this backwards E, I'm sure we talked about this before. This means that there exists, okay? There exists an object which I call 0. I want to be very clear here. This object that I call 0 does not always look like something full of zeros, okay? I know you're used to this being this 0 vector being a column full of zeros, or a matrix where every entry is 0. That is not always the case, okay? We will definitely see, and I will on whatever exam comes up next, have an example where your 0 vector is not a item in your vector space that is full of zeros, okay? Again, remember what I said. We're kind of taking everything you know about math and we're kind of like turning it upside down a little bit. So you're familiar with all of these things, but they are not identical to what you are used to, okay? So there should be an object in there that I call the 0 vector, okay? Such that if I add this object, which is not always all zeros, to an item that is in my vector space, it should be the same thing as if I were to swap the order, which is coming from that commutative property of addition, and I should always get out my original vector. Okay, so the 0 vector holds for us the additive identity. Okay, this is the additive identity. It works such that if you are to add it to anything in here, you're just going to come out with that object itself, right? So there exists something in our space that we call the 0 vector, such that if I add it in any order to any object in my vector space, I will always get out that original object. Now if I read this as is written, there exists a 0 in V called the 0 vector for V, such that 0 plus U is equal to U plus 0 equals U for every U that is in V. Okay, so that's how we would typically write that. The previous explanation was a more layman's term. This is what this is how it works, this is how we interpret this sentence, right? So the last axiom that we have for addition, again, there's 10 axioms total, right? So these are the 4 so far. So again, closure under addition, commutative property of addition, associative property of addition, an additive identity, right? You add something to your object, you will always get your object out. And the last property that we have for addition is that for every vector inside of my vector space or my potential vector space, there is a unique, right? So again, that backwards E means there exists. The exclamation part with it means a unique. This is called a negative U, right? So again, it's not actually called the negative U. It's called the additive inverse, okay? So for every object U in V, there is a unique additive inverse in V, such that if I were to add the additive inverse to a vector in any order, right, coming from that commutative property, I will get out the 0 vector. So again, this additive identity, it is highly possible that it is not just all the items that are in U with a different sign. Okay, that's the easiest case. That's the case you guys are the most familiar with. Okay, it's very possible that it is something completely different. In fact, I'm going to show you one where the 0 vector is not the standard 0 vector, and the additive inverse is not your typical, hey, let me take everything in this vector and change the signs on it. Okay, that's the ones you are used to, but that's not the case all the time. Okay, now when I'm adding this vector to its unique additive inverse, I am getting out the 0 vector. The same 0 vector here, not just something full of zeros. I'm getting out whatever the 0 vector that I had for my vector space. This 0 vector is always the 0 vector for this vector space. So if I'm adding things to their unique additive inverses here, I should always be getting the same 0 vector that I have in 4. Okay, so again, to read this notation, right, I did say I was going to introduce you guys to this mathematical notation. You are in a higher level math course now. For every U in V, there exists a unique negative U or additive inverse in V, such that U plus its additive inverse is the same as the additive inverse plus U equaling the 0 vector. Okay, so for every object that I have in my vector space, there's a unique opposite. Okay, and I don't want to say opposite because it's not really an opposite, right? It's an additive inverse. That it has the property that when you add it to the vector that it's associated with, you will get the 0 vector out. Okay, so these are the 5 axioms that we have for addition. So again, one more time, I've been going over these each time. Just to reiterate: closure of addition, commutative property of addition, associative property of addition, an additive identity exists for my space, and every vector, every object in my space has its own unique additive inverse. Okay, so that's what we have so far. So now we're going to move on to the next 5 axioms. So it's not going to go 1, 2, 3, 4, 5 again. It'll be 6, 7, 8, 9, 10, right? But the last 5 are the scalar multiplication axioms. Okay, so again, this additive inverse is called the negative of u. Okay, that's what we call it. You can call it the additive inverse as well. Additive inverse is actually the property that it satisfies. Its name is negative u. Okay, so for number 6, the beginning of the scalar multiples, if I have a real number, okay, k is an r, so k is a real value. Again, it can be pi, it can be 1/2, it can be 0.23896, it can be 2/3, it can be square root of 28, right? It can be, it's a real value. U is in V, so it is an object in V. I'm hesitant to call it a vector because we're proving it's a vector space, so it's not technically a vector yet, right? But U is an object in V, whatever the collection of things in V is: vectors, matrices, functions of a certain type, transformations of a certain type, etc., right? It's a collection of objects. Then K times this object in V is still going to be in V. So again, we're used to this axiom as well. This axiom is the closure of scalar multiplication. So if I take a scalar and I multiply it times my object in V, that scalar multiple of the object is still inside of that space that I'm in. Okay. Here, if I add 2 vectors together and I multiply them by the scalar, the scalar should distribute across the vectors, right? So this is the distribution property of scalar values. Okay, so it should distribute across my my parentheses here, my addition. Okay. Here, if I have 2 scalars that I'm adding together and then multiplying times u, so this is still a scalar multiple of u, this should be the same thing as me multiplying u times the scalar k and m and u times the scalar m and adding those 2 results together. Okay, so here this is the distribution of a scalar. This is the distribution of a vector across scalars. Right. Here, this is the associative property. If I multiply m times u, right, so if u is a scalar multiple by m and then I multiply it by the scalar k, that's the same thing if I have a km scalar multiple of u. Right, so this is the associative property of scalar multiplication. And the last one is the multiplicative identity, which is this 1 here is not some weird object, it's a regular 1. Okay, 1 times my object is going to be the same thing as just the object. It's the multiplicative identity. It is 1 here. It does not change. It will not take on some weird values. You don't have to worry about this. This does not take on unique forms. Okay, it's your standard 1 here. Okay, so again, the 0 vector and the additive inverse are unique vectors to the vector space. Okay, so the way that they look, this is 1 single object. This takes on a general form for all of your vectors in your vector space. Okay, so now that we have those 10 axioms, let's go through an example. So again, I want to weird you out, so we're going to choose a very strange example that gives you a different definition of addition, a different definition of scalar multiplication, and has a 0 vector that is not your typical 0 vector, and an additive inverse that is not your typical additive inverse, right? So I wanted to choose something that would be new to you, because you've probably seen this, you probably don't remember it, but you've probably seen it in like a geometry class or something to that effect, of these 10 axioms being shown for something like the real number system. Okay, so going through a standard definition of these is easy. If you want to see one of those, look in your textbook in section chapter 7.1. They go through a couple, I think, of ones that work out very, very nicely, that are very, very standard. So I want to choose a non-standard one so you can kind of see that the things that you are used to are not always the norm, right? So let V, so right now we're going to define what V is. So let V, this set of objects, be the set of all ordered pairs of real numbers. Everything in here is an ordered pair for this set. Okay, I'm saying this because I give out other examples, or I give out problems, and then every person goes through the homework set or the classwork set, and they're looking for ordered pairs everywhere. It's not always ordered pairs. For this example, the collection of things is ordered pairs. There may be another problem where I ask you to define things that are all matrices. So if you start giving me ordered pairs for things that are matrices, that doesn't make any sense, right? So for this example, our set of objects, our collection, is a collection of ordered pairs. Now these ordered pairs that we have are special, right? They're special because they're real numbers, and the way that we define addition and scalar multiplication is as follows. And this is what makes our potential vector space unique. If I take two vectors, two objects from this space that I have, this set of objects, and add them together, you can see that the standard definition of vector addition holds, except you're adding 1 to everything. So normally it would be just u1 plus v1 and u2 plus v2, and that's how you would add two objects together. Here we're going to do the same thing. We're going to add the first items from each vector or object together, and then increase it by 1. Same thing with the second portion. We're going to add the second numbers from the ordered pair together, and then increase it by 1. And that's how we're going to define addition. Okay, it's not that strange. So if this was 1, 1 and this was 2, 2, instead of adding them together and getting 3, 3, I would get 4, 4. Just I'm bumping the numbers up by 1. Okay. Now for scalar addition, it looks like this holds as well. Sorry for the boldface. This should just be regular u1, u2. But here we have scalar multiplication, and we're defining scalar multiplication like normal. We're not changing our scalar multiple. Okay. So if I want to multiply a vector in here, an object in here, they're ordered pairs. So I'm just multiplying each element in that ordered pair by k, just like normal. Okay. So our job here is to determine whether this set we have, the set of ordered pairs, is a vector space or not. Okay. So the way we're defining addition and scalar multiplication is going to be what determines whether or not this is actually a vector space. Okay. So if I define addition in this way, am I still a vector space, or am I no longer a vector space? Okay. So we need to do this by checking each of the 10 axioms. You cannot just check a couple. You got to check all of them. Okay. Because generally what's going to happen is I'm going to say which one of these things fail to hold, right? So again, we're going to check all the 10 axioms, and any of the axioms that fail to hold, if any, we will list out. If none of them fail to hold, then this is a vector space. Okay. So we want to identify the zero vector and the additive inverse. So at the end of this, right, you would check your 10 items. Okay. If there are axioms that don't hold, you would list those. You would tell me what your zero vector is, and you would tell me what your additive inverse is. Okay. So let's go ahead and get started. So again, these are all proofs. If you're not starting these off by writing proof with an underline and then beginning in a standard proof manner, I will be taking off points from your assignments. Okay. That's the way proofs are written. You don't just start writing a paragraph, right? There needs to be math. It needs to be labeled. You need to identify that you're starting a proof, right? So again, let's call our objects into existence. I know I need 3 vectors and how many scalars? That's right, we need 2. So I count out 3 vectors. I got 3 objects inside of my set of objects and 2 scalar values. Okay. And U looks like this, right? Because remember, there's sets of ordered pairs. So this is what U looks like. That's what V looks like. And that's what W looks like. Again, if I was talking about 2 by 2 matrices, U would need to be a 2 by 2 matrix. V would be a 2 by 2 matrix, and W would be a 2 by 2 matrix. But I'm talking about ordered pairs. So this is what my objects look like, okay? And I am defining, as given above, vector addition as adding the components together just like regular, but increasing it by 1. And scalar multiplication is a typical scalar multiplication, okay? So the first axiom, U plus V. You cannot just write U plus V equals V plus U, done. That's what you're trying to show to the reader is true, so you need to show that that is true. I get that probably like from 80% of my students on their first go around. So again, you guys have done this before to an extent, so we need to just show that adding these two things together, or at least for the first one, remember this is closure of addition. So U plus V is really just going to look like this, okay, because that's how you define addition. And look, this is 1, 2. It's an ordered pair, right? It's an ordered pair, and that's what are things in V. So if I add two random objects out of V together, I still get an object that's in V, because what is V? It's a collection of ordered pairs, okay? 2 is the commutative property, that if I add U plus V together, it's the same as V plus U. So I was mistaken briefly here, as I thought that that's what 1 was. So again, here I can't just write U plus V is V plus W is V plus U. I'm done. It doesn't work that way. What is U plus V? U plus V is that thing. Okay, that's how I define addition. It's U1 plus V1 plus 1, U2 plus V2 plus 1. That's what that is. I'll do that. Okay. Now I'm trying to get to V plus U. What would V plus U look like? Well, if U is first, then look at the U's are first. But if I'm trying to get to this property where it's V plus U, I got to move the V's in front. It's really that easy. It's not super difficult for this portion, right? So U's are in front because that's what U plus V looks like. So if I swap the orders of the U's and V's, well, hey, guess what, you guys? That is what V plus U looks like. So now I have U plus V equals, at the end is V plus U. So if you get stuck, if you're here and you start to work your way down, you can always think about where you're trying to go and work up from there, and you should meet in the middle. So we have U plus V equals V plus U. So again, at the end, you always want to have like a small sort of statement saying what it is that we just shown, right? So we just did some work here. What is that? Well, I just showed the property of the commutative property of addition, right? So I showed U plus V is V plus U, right? Here I'm saying therefore I showed that the closure property of addition holds, okay? So here we have U plus V plus W. So again, what I'm trying to do is I'm trying to show the associative property of addition. So I'm trying to show that if I add V plus W together first and then add in U, it'll be the same thing as if I were to have added U plus V first and then W. So I'm adding U to these things. So I'm just going to have a standard U, U1, U2, plus this is what I'm adding together first. So it's going to look like this thing. So I'm going to have a U1, U2 plus this is being added first. I'm not adding this in yet. I'm adding this in standard off top, right? So it should look like that. Okay. So U1, U2 plus something that has already been added together, right? So V's and W's, V1, W1 plus 1, V2 plus W2 plus 1. So then the next thing I'm going to do is I'm going to add this to this. So remember what it means to add things together. The first two elements add together plus 1. So here, the first element plus this whole first element of this vector, right? This is one vector right now. So this first element plus this first element plus 1. Second element plus the second element plus 1. Okay. So I have u1 plus the first element plus 1 more. So this whole thing here is the first element of my result, right? Same thing. Second component with the second component. So u2 plus v2 plus w2 plus 1 more, right? First component plus second component plus 1. So then on the next one, I can simplify that because I'm basically just adding all the 1 parts together. 1 plus 1 will be 2. All the second components together, 1 plus 1 will give me 2. But remember where I'm trying to get to, right? So if you notice, it took me 3 steps to get here. You should not write this in the very first line you have is this thing here because you haven't shown me how you got here. Okay, again, these proofs need to be very thorough and you need to really show your work. Okay, so try to avoid the jumps in computation. Okay, so write things out. Okay, so for here, I'm trying to get to u plus v. I want u plus v plus w. So just like this was a single component here, like this, right? A single vector, I'm going to need u plus v to be a single vector. Because remember, I want u plus v plus w. So just like u was alone here and had u1, u2, I need the w alone and being w1, w2 out here. Okay, so what I'm going to do is I'm going to start trying to separate things. I got the u and the v's already together because remember, I'm trying to rewrite this as u plus v. So I have u1, v1. I'm going to need to steal a 1 from here, right? And a 1 from here. So u1 plus v1 plus 1 because that's what u plus v looks like, right? That's what u plus v looks like, right? And the second component plus my w, which is what happens when I have, when I'm adding things together, right? So when I take u1 plus v1 plus 1 and I separate out that vector that I added in, well, that 1 goes away because that's what it looks like when I add it to another vector, right? Just like I did up here. So when I pull this out, that 1 goes away because I'm undoing this thing, right? So this looks like u plus v and then adding in w. All right. So again, a little strange because you had to undo some work, which is why you don't skip steps here. You need to show everything. It should flow very, very logically. If you read this way, it makes complete sense. If you read it this way, it makes complete sense. If you start skipping these lines, it doesn't read so well from one direction to the other. It needs to flow very well in both directions. Okay. So that was the third property, the associative property of addition. Our next property is the one that I warned you against at the very beginning, right? It is the additive identity. It is that 0 vector. Okay. So here I'm going to pause and I want you to think of what the 0 vector would look like. So you need something so that when you add it to a vector, you get out your original vector, right? This is property 4, the additive identity. If I add this vector to any vector or in the other direction, I will get that vector out. Okay, so remember, we are adding things by adding a 1 to the end. So what should my 0 vector look like so that when I add it to anything under this property of addition, right, this definition, I will always get out u1, u2. Okay, so I'm going to shut up for a second, pause the video, please, and I want you to try to make your own 0 vector and then just see how close you were to what the actual 0 vector is going to be. Okay, so in 1, 2, 3. Okay, so hopefully you pause it. If not, you probably enjoyed the silence where I wasn't talking anymore. So let's go ahead and move forward and see what we have, right? So again, here just to close this one out, we have our summarizing statement here. Therefore, u plus v plus w is the same as u plus v plus w, right? So that's what we just showed, this associative property. So for a 0 vector, your 0 vector should be -1, -1. Well, would you look at that? There's no zeros there at all. Okay, But if you add that to any vector, using our definition of addition that we have here, you will get out the original vector. So again, right, our 0 vector here is not all zeros. Okay, so let's just prove this. Okay, again, that's what we're doing, right? So what is u 0 plus u? I'm taking the first element of my 0 vector plus the first element of my u vector and adding 1 to it. Same thing with the second components, and look, -1 plus 1 goes away. Okay, so if you notice here, I swap things around, but why did I do that? Well, because we also need to show that 0 plus u is the same thing as u plus 0, right? So here I have the first element of u plus the first element of 0 plus the 1, right? So this 0 plus u is equal to u plus 0, which is what we're trying to show. And I want to show that both of these are equal to just u, because, so that's where I do this next line, right? -1 plus 1, -1 plus 1, they go away. I'm left with u1 and u2, which is u. Therefore, what did I show? 0 plus u is the same thing as u plus 0. That's why I swapped these around, okay? Which is the same thing as u. So I showed the whole additive identity property, okay? So that's what you'll need to do for 4 and also for 5. Do you remember what 5 was? That was our additive inverse, okay? So again, this negative u is not the same as u times -1. That is not what the additive identity is, okay? So here, my negative u, again, this is not -1 times u. It is not -1 times u. A lot of times it is, but for this case, it is not. This is an object that we call negative u, right? My definition for this, so again, let's look at what I need to prove. I need this thing so that if I add it to any vector, I get out the 0 vector. And so remember, what is my 0 vector? My 0 vector was -1, -1 in this case. So I need something that whenever I add it to any standard vector, right, its additive inverse, I will get out -1, -1, because that's what my u vector, or I'm sorry, that's what my 0 vector is. Okay, so this additive inverse is associated with this additive identity. They go together, okay? So this is what I need for an additive inverse. So whatever my u1, u2 elements are, I need them to be the opposite value, and I need to, from that, subtract 2, okay? If I do that, then whenever I add u to negative u, I will have, again, u is first, so u1, u2, and then second is this negative u, so I'm taking negative u, -2, negative u, -2, and then remember my definition of addition. I take the first components and I add 1. The second components, I add them together and add 1. Okay. So I also need to move stuff around, right? Because I also need to show that u plus negative u is the same as negative u plus u, right? So just to go back one more time, this was a 2-part, right? 4 and 5 are the only ones that are like that. 0 plus u is u plus 0 is u. U plus negative u is negative u plus u is 0. These are the only two that have kind of like a twofer like that. You need to do 2 different things in one. Okay. None of these other ones have that. Just 4 and 5. Just the 0 vector and the additive identity. So it's easy to remember that because they're the weird ones, right? So here I'm swapping the order. Okay, negative u, -2 is first. Negative u, -2 is first. u1 is second. u2 is second. And this plus 1 is still last because I'm still adding 2 things. And that's what it looks like to take the negative of u plus u itself. So now I can actually do the math and simplify this. And you should notice that negative u and the u ones, those cancel, right? The u stuff cancel. -2 plus 1 simplifies to -1. So I'll be left with -1, -1, which is, hey, it's my 0 vector, okay? That's my 0 vector. So, if I take the additive identity and I add it to U in either order, okay, then I will get out my 0 vector. So U plus -U is the same as -U plus U, which is my 0 vector, which again, this was not -1 times U, and this was not just a bunch of zeros. And it's like that because of how I define my addition, right? I'm adding this stupid, weird +1 to everything, and that's my definition of addition. So that's why things are different here, okay? So now let's move on to property 6. So we've done all of our addition stuff. Now we're going to get into our scalar multiplication. So if a scalar times U is going to be KU1 times KU2, which is how I defined it, which is a ordered pair, which is what things in V are, right? So that means that KU is in V, and that's what I needed, was that scalar multiples of objects in V stay inside of V, right? So that's good. So the next one is 7, which is if I have a scalar times two vectors that are being added together, right? So what I need is that this thing distributes across and it comes out to be equal. So the definition of addition here is that I add these two things. So the first component's +1, the second component's +1. So when I distribute this k, you should notice that I got, again, k times everything, which is not the same thing as k times u plus k times the v plus 1, k times the u2 stuff and the k times the v2 stuff plus 1, right? These are different, right? They're not the same thing. So this one that is not equal to is what k times u plus k times v should be, right? So again, this is why it's important to sometimes go in one direction and then go to the end and work your way up to see if they match up or not, right? So I'm never adding an extra scalar multiple. It's always +1. So this is what ku plus kv looks like. This is what I get when I add u plus v together and then multiply by k. They're not gonna come out to be the same thing, okay? So axiom 7 actually does not hold. So right here and there, I can say, boom, this is not a vector space, okay? So since when the axioms don't hold, it's not a vector space. That does not mean that I can stop going through the axioms, however, because I was asked to list all the axioms that fail to hold, okay? And then also I have to identify what the 0 vector looks like, which we've done, and what the additive inverse looks like, which we've done, okay? So we made it all the way to 7 before we ran into a problem. So hopefully that's the only one that doesn't hold, but let's see, maybe there's more, okay? So our summarizing statement here, right? So therefore, k times u plus v is not the same as k times u plus k times v, okay? So axiom 7 does not hold, right? So let's look at 8. 8 is that if I add two scalars together and multiply it times u. So again, this should be the same thing as me distributing u across these scalars. So let's see what this looks like, okay? K plus m times the first component and k plus m times the second component. So if I distribute the terms across, this is ku1 plus mu1, ku2 plus mu2, which is not the same thing as ku1 plus mu1 plus 1, which is what happens when we add stuff here, right? So this is not equal to this. Therefore, axiom 8 does not hold. Okay, so there we go. We have two axioms so far that are not holding. So 9 is k times mu. So again, this is what's happening first. So m times u1, m times u2. The next step, now I can distribute this k across, which is the same as k times m times a vector u. Therefore, this left-hand side is equal to this right-hand side. Okay, no problems. Okay, for 10, I have 1 times u is 1 times the first component times 1 times the second component, which is just u1, u2, which is u. So the multiplicative identity exists, and it's 1, right? It's never a weird thing. Therefore, 1u equals u. Therefore, we can say that V is not a vector space, since axioms 7 and 8 fail to hold. I did not, at the end of this, say, oh, hey, by the way, this is my 0 vector and my u vector, or negative u, which is fine because it's an example and I'm just doing stuff. But if I ask this on an exam or something like that, I wouldn't want you to state the two. I do, however, consider this as it being stated. You told me what the 0 looks like, and you told me what a negative looks like. You don't have to repeat it at the end, although it would be nice because it makes it easier for me to grade. I'm fine with you throwing it in here, okay? So, which you should be doing anyways. So that's the reason I put it, is because some people don't write what they are and they just start doing math, okay? So let's do some examples of some common vector spaces. So these are things that you're used to, okay? Vectors, again, are not always columns of numbers, right? They can be different things, as I stated at the beginning. Okay, so some common vector spaces is Rn. So vectors of size n that have real value entries. Okay, we call this Euclidean n space, is the standard term for it. So real Euclidean n space. Here we are giving the standard definition of addition and scalar multiplication. So the way we've been adding things normally, and the way we've been multiplying things by scalars multiply, right? So the standard method of adding and multiplying stuff is a vector space, right? The Euclidean n space. This is probably the most important vector space, actually. Okay. The Rm by n, you should be familiar with this. So these are real valued matrices with m m rows and n columns. So again, with the standard definition of addition and scalar multiplication. So if you've noticed, we were in this last example in R2, right? We had ordered pairs. However, our definition of addition was different, and that's why it was not a vector space. Okay, the properties didn't hold true. Now that doesn't mean that there's other weird definitions of addition or scalar multiplication that do hold. Okay, there are. I'm 100% going to give you some either in your classwork or an exam, right? I'm not going to tell you which, but you will come across them in this class. Okay, probably in your homework as well, right? So there are weird definitions of addition and scalar multiplication that do hold true for vector spaces. Okay. So another common one is Pn. So you should definitely remember this because you're going to see this a lot in this chapter and for the remainder of this chapter. So Pn is the set of polynomials that have up to a degree of n. Okay. So if you are in P3, then any second degree polynomial is still inside of that space. Any line, any first degree polynomial is still in that space. And any third degree polynomial is also in that space. Okay. So here for Pn, you have real valued coefficients in the way that you regularly add polynomials together, and the way that you generally multiply them by a scalar value are our definition of addition and scalar multiplication. Okay. So here R infinity is just like Rn. It's the real Euclidean space. It's just that your vectors have an infinite number of entries. Okay. So infinite sequences of real numbers. Vectors with infinite components. All right. Again, with the standard definition of addition and scalar multiplication. Okay. Here TMN, this is the set of all linear transformations from Rm to Rn. So it's giving you the dimension of the space you're going from that you are going to, right? Again, with the standard definitions of addition and scalar multiplication, these are also vector spaces, right? So remember, what is a linear transformation? It is you taking a vector and multiplying it times a matrix. That is very similar to what these things are, okay? And in fact, polynomials are very similar to the real Euclidean space, right? Because the coefficients here are related to these things. So we're going to go over that in chapter 9, actually, when we go over what's called isomorphisms, right? Which is two vector spaces that are pretty much identical to each other, right? They have different names, but all the components and all the way that things work inside of them are pretty much identical, right? So these would be an isomorphism because the coefficients here you can just write out as vectors. Okay, we've actually seen that. I've given that to you in exam problems already. These matrices are the same as the matrices you would have here for a linear transformation. We've seen plenty of times already, change of basis, those sort of things, where a matrix and a linear transformation are very, very similar. These are also what are called isomorphisms. So again, you don't have to worry about that now. That's just a preview into the chapter 9 stuff that we will be going into. Okay. Here, Cn to the AB, you should remember this from calculus 2. This is the set of what are called smooth functions. Here, n can be any value. It can be an infinity even. An infinity means it's infinitely smooth. So what does smooth mean? It means you are continuous over this interval given, and your nth derivative is also continuous. So it has to do with continuity and derivatives. So if this was C2 over, let's say, all of R, then that means that it's all the functions that have a continuous first and second derivative over the entire real numbers. Okay. Now the third, fourth, fifth, etc. derivatives in that case may not exist, or they may not be continuous, or whatever the case is. Okay. But this is a calculus definition here, right? And smooth means you're differentiable this many amount of times, and all of those derivatives are continuous. Okay. So continuous up to the nth derivative over the given interval, right? So it could be a closed interval, it could be all of R, it could be Z even, right? Which really doesn't make any sense, but it can be, whatever the definition of the interval is here, right? So let's recall our definition of a subspace is that if we have a subset of a larger set, which constitutes a vector space. So again, here, this is a set of objects, satisfies those 10 axioms. If we take a subset of those, okay, S is a subset of V, then S is a subspace if the zero vector, in this case now it can be a weird zero vector, before it was always just all zeros. So here, that zero vector that we have for this vector space is also in this collection of objects we call S. The zero vector for the vector space is in S. If I take two vectors in S and I add them together, they will stay in that subset also. Okay, it's closed under addition. And then for every vector in S, if I take a scalar and I multiply one of those objects in S by a scalar, I will still be in S. I'm closed under scalar multiplication. That is our definition of a subspace, right? A subspace. So now let's take a theorem to relate the two. The subspace is S containing the zero vector, and the subspace containing the entire vector space itself. Those are called the trivial vector spaces because they're boring. I already know V is a vector space. It's a subspace of itself, right? Here, this is the smallest subspace I can have, which is just the zero vector, because if I add 0 plus 0, I'm still inside of 0. And if I multiply anything by 0, I'm still 0, right? So it's a trivial subspace. Sorry, this is called a trivial subspace, not the trivial vector spaces. So it's because they're boring subspaces. Okay, and that's it. That's our definition. We got through one example in less than an hour. These things can be very long until you get good at them. Make sure you practice. I would go over this video again. I would try to do that entire example that we did, those 10 axioms with the ordered pairs. Try and do it yourself without looking at the notes and see how close you can come. It'll make having to do this later go a lot faster and be a lot easier if you try something that already has the solutions for it. Okay, so that's my suggestion to you. Good luck. See you on the next video.